Alright, so we continue with a case of a weak electrolyte. So I give the let's do the example of acetic acid dissociating in water to give protons and conjugate base acetate. Now, for a weak electrolyte, not all of the molecule here, the acetic acid molecule, will dissociate into H plus and the acetate. Now, this is a theory by Arrhenius. So there is this concept of degree of dissociation. Alpha is equal to the concentration of a proton at equilibrium, right after he has dissociated, over the initial concentration. Now, for a weak electrolyte, alpha is much lower than 1, right? If it's completely dissociate, if the molecule completely dissociate, then alpha is equal to 1. So with a weak electrolyte, alpha is much lower than 1. Right, so the weaker the electrolyte, then the lower the alpha, and thus, because this is an equilibrium expression, there is an equilibrium constant, then the K will also, the equilibrium constant for this reaction will also be low. Right, Ka here is dissociation constant of the acid. So we can express the dissociation constant as the concentration at equilibrium of the proton times the concentration at equilibrium of the acid, of the conjugate base, over the concentration at equilibrium of the acid. Okay, so these two have the same concentration because one molecule will dissociate into one molecule of proton and one molecule of the conjugate base. So I can fill this here if I simplify this expression into C, so the initial to be value of C, right? So here, then the concentration at equilibrium for the proton would be alpha times C. Okay, now this will be the same as the concentration of the acetate, also alpha times C, and here the remaining amount of undissociated acid would be 1 minus alpha times C. Okay, I can simplify this into alpha squared times C over 1 minus alpha. Okay, because I remove 1C here. Okay, right. Now you notice that I've expressed this in terms of concentration instead of activity, and this is because for weak electrolyte we assume that the concentration of the ions are very low because the dissociation constant is low. So alpha is near, gamma here is near to 1, which means that activity is very close to the concentration. So this is the case. You can use this approximation or this theory when the K equilibrium constant is very low, or in other words, for weak electrolyte. Now, Arrhenius also proposed that alpha is equal to molar conductivity over molar conductivity at infinite dilution. Okay. Now, just to remind you that molar conductivity is equal to the kappa over C. Kappa is what you normally get from the instrument conductivity probe. Now, having known this from the previous paper and this Arrhenius proposed, you can substitute this into this form now, substituting alpha with the expression of molar conductivity, and you get this expression, and then you can derive this into a much simpler expression to get a linear relation in which 1 over molar conductivity equals to 1 over molar conductivity at infinite dilution plus 1 over equilibrium constant times the molar conductivity at infinite dilution square times molar conductivity times concentration. This is in your book. Just look for it. And this linear expression, you will have this as the intercept and this as the slope. So when you do an experiment, you will vary the concentration. And you will plot the molar conductivity times C versus 1 over the molar conductivity, and you will have a straight line. From this straight line you can get the intercept, you can get the molar conductivity at infinite dilution, and you can get by calculation also the slope and finally the dissociation constant. You will do this in your lab. Okay, great. I hope that is clear, and good luck.